Hi, my name's Jeff Dean, and I'm Math Dad. I'm here to help you help your kids understand math. In mathematics, there are connections everywhere, but often we don't see them because we rush to try to find answers quickly. Hey, did you get that answer yet? I didn't get that answer yet. Did you get that answer? I got it faster than you. When we rush to find answers, we often miss the critical connections that help us see the big picture of math. Today, I'm going to show you a connection between three problems. I want you to take a second and think about, how would you solve these problems? Would you do the exact same thing, or do you have some memorized method that you've used for each one individually? If all you've done is memorized processes and procedures to get answers, you're probably missing the connections. Check this out. Let's start with 56 divided by 4. Let's represent this as a picture. In this picture, we can see that 56 is made up of 5 tens and 6 ones, and 4 is just 4 ones. And what this division problem is really asking us is how many of these 4s can be placed inside this 56. So let's take a look at how many times we can take 4 in this 56. Well, here's one group of 4 right there. And here's 2, 3, 4, 5, 6 groups of 4, 7, 8, 9, 10, that's 11 groups of 4, 12, 13, and 14 groups of 4. There are 14 4s inside of 56. Therefore, 56 divided by 4 is equal to 14. We're going to use this exact same model to make some connections. In this problem, we have 1 3/4 divided by 1/8. Let's represent this as a picture similar to the last problem. In this picture, we can see we have one whole, and this is 3/4 of a whole. These dotted lines are to help us see how big the whole is. So this is 1 3/4. Over here, this is the entire whole, and we just have 1/8. So what we want to do is figure out how many of these 1/8 pieces will fit into our 1 3/4. Well, we might need to draw our 8s in here so that we can count them all up. Each of these pieces is now 1/8. So we can see inside we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 of these 1/8 size pieces inside of 1 3/4. So 1 3/4 divided by 1/8 is just 14. I'm starting to see how these seem to all be the same. So let's take a look at a problem that involves decimals. We have 11 2/10 divided by 8/10. Let's use a model similar to what we just looked at. In this model, we have 11 2/10. Each square represents 1/10, and we're dividing that by 8/10. So again, our goal is to see how many of these 8/10 can fit inside 11 2/10. Let's check it out. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10 of these 8/10 fit into this. Here's 11, And then we come down here and we can see we have 12, we have 13, and we have 14. So it took 14 of these 8/10 to fill up this 11 and 2/10. So what was all this move the decimal, flip the fraction, multiply business that I was taught? You, my friend, you were taught rules, not connections. I want you to understand the big picture of mathematics. The connections are made in the inefficient methods that we use to introduce concepts. All right, so if this is a connection, how does this apply to math that I might do later, like in high school or something? This method of division starts laying the groundwork for doing repeated subtraction. You can see in all those methods, all we were actually doing was subtracting one chunk at a time until we depleted everything. And that is how we can connect this to things that we learned in algebra. When we take a look at 56 divided by 4 without pictures, we see that all we're really doing is subtracting 4 over and over again. I can subtract one 4, that gives me 52. I can subtract a second 4, and that gives me 4. I can subtract a third 4, and that gives me 44. And then I can subtract a fourth 4, and that gives me 40. Now at this point, the hope is that we can see there's 10 more 4s left. So if I subtract 10 4s out, that's 40 minus 40, which is 0. And I've used all the 4s. So how many 4s did I use altogether? 14. I can use the same idea to do this division problem involving algebra. If I have x squared plus 7x plus 12, and I want to repeatedly take out an x plus 4, well, I'm going to take out one x plus 4, and that would leave me with x squared plus 6x plus 8. Then I'm going to take out a second x plus 4, and that will leave me with x squared plus 5x plus 4. And then I'm going to take out a third x plus 4. And that leaves me with x squared plus 4x. And there isn't anything left over here. So now I have x squared plus 4x. And at this point in algebra, hopefully we'll see that we have x more x plus 4s. And x times x plus 4 is x squared plus 4x. And when I subtract, I get 0. So how many x plus 4s did I take out? Well, I took out x of them, and I also took out 3 more. And that is the reason why x squared plus 7x plus 12 divided by x plus 4 is x plus 3. Wait a minute. Are you trying to tell me that division is just division, regardless of the type of numbers that I see? That's exactly the connection that I want you to make. If we rush too quickly to formulas and procedures, then we rob our kids of understanding. Hey, slow down. I'm trying to make some connections here. It's in these inefficient methods where all of the connections exist. If we ignore the connections, then everything just seems like an isolated rule. It's no wonder that kids think math is filled with tricks and that they can't figure it out unless they know the trick. That's what we want to avoid. We want our kids making connections. My name's Jeff Dean, and I'm Math